Hi. So today we are going to derive the formula to find the sum of first n natural numbers. So natural numbers are represented as capital N and they start from 1, and after that every next number is one more than the previous number. So it will be 2, 3, 4, 5, 6 and so on, right? So this is the set of natural numbers. So today what we are going to learn is how to find the sum of natural numbers. So if I have to find the sum of first 6 natural numbers, this will be the case, right? These will be the first 6 natural numbers, right? And if I want to add them, yes, since there are only 6 numbers, we can add them manually without using any formula. So it will be 1 plus 2 plus 3 plus 4 plus 5 and plus 6, 21, right? So the sum of first 6 natural numbers is 21. This was very easy because we had only 6 numbers and all of them were very small, right? What about if we have 100 numbers or 200 numbers? So how to add them? So to add them we have to have a formula. So today we are going to derive that formula, and that we are going to derive step by step so you understand the logic behind that formula and it will be easier for you to remember it. So let me remove all this addition work. If I remove this addition work and let me keep this sum at one place so that we can compare. I'm keeping it only for comparing purpose, right? So to derive that formula, I'm going to do one thing. So the first step I'm going to do is I'm going to group these numbers. So this is the first group. Then we have this as a second group and this as a third group. What I have done, I have grouped the first number with the last number of the series, and the second number with the second last number of the series, and third number with the third last number of the series. So what I get by doing this, if I add the numbers of each group, I'll get 1 plus 6 as 7, 2 plus 5 also gives us 7, and similarly 3 plus 4 will also give us 7, right? So now we have got 3 groups of the numbers where sum of each group is 7, and now the task of finding the sum of the series becomes very easy. Now we have 3 groups, right, and sum of each group is 7, so the total sum will be 7 multiplied by 3, that is 21, right? See, we have got 21 over here, and earlier also we had got 21, right? So this proves that this method works. Okay, now let me generalize this method. If I have a series from 1 till n, and we were supposed to find the sum of first n natural numbers. So the series will be something like 1, 2, 3, 4, 5, and here we will have n minus 2, n minus 1 and n. Like series will start from 1 and it will end something like this, n minus 2, n minus 1 and then n. So again, if I group these numbers in the similar fashion, the first number with the last number and second number with the second last number and third number with the third last number, fourth number will get grouped with a number somewhere over here, and the fifth will be grouped with its previous number, right? So how many groups will we have? Number of groups will be n by 2, right? If this n is an even number, and if this n is an odd number, we are going to discuss it later in the same video. So if n is an even number, number of groups will be n by 2, and the sum of each group will be n plus 1, isn't it? Right? In this case also, the group which I have linked in green color, this n minus 1 plus 2 will also give you n plus 1. Similarly, this group where I have grouped 3 with n minus 2, n minus 2 plus 3 will also give you n plus 1. Yeah, that is why we have grouped them, because in each group we get the same sum, right? So what we have now, we have n by 2 groups where each group has sum as n plus 1, right? So what will be the total sum of this series? Total sum of this series will be n plus 1 multiplied by n by 2, right? N plus 1 is the sum of each group, and we have total n by 2 groups. So this will be the formula to find the sum of first n natural numbers. So this is the formula to find the sum of first n natural numbers, right? And then we had a doubt when the number of terms is odd. So again we are going to take a small example. So let me write numbers from 1 to 5. So 1, 2, 3, 4 and 5. We have odd number of terms, right? And what we have to do next? Yes, we have to group the first number with the last number. Of course, we are following the same procedure. And then we have to group the second number with the second last number, right? And then we have this middle number left behind, right? What is the sum of these groups? 1 plus 5 is 6. 2 plus 4 is again 6, right? We have got two full groups where sum of each group is 6. And what is this? This is 3. 3 is nothing but 6 by 2. It is half the sum of the groups, right? So we have two full groups where the sum is equal to 6. The sum of two groups will be 2 multiplied by 6, that is 12, right? And then we have one number. We have 3 which is left behind, and this is what? This is actually the half of the sum of each group, right? So how many groups we have now? We have two full groups and one half group. So to find the sum of the series, we have to do this 12 plus 3. So the sum will be 15, right? And what is our formula? Formula is n into n plus 1 by 2, where n plus 1 is the sum of each group and n is the number of terms, right? So in this case, we have number of terms as 5, right? So it will be 5 multiplied by 5 plus 1, which is 6 by 2. This is equal to 5 6 are 30 by 2, which is equal to 15. So when we have odd number of terms, then also we are getting the same result, right? The reason behind that is the term which is left behind is exactly the middle term of the series, and the value of that term is exactly the half of the sum of the each group. So that is why it gets covered in n by 2.
In this tutorial, I'm going to be doing a proof by mathematical induction. So I'm going to be proving that 1 plus 2 plus 3 plus all the way up to n is equal to n times n plus 1 divided by 2. So what we want to do first is we want to check the base case. So this will be the basis step. And we're checking the base case. We're checking the most simple basic case that we can come up with here. And it's going to be when n equals 1. And we're just going to check that for n equals 1, the left-hand side and the right-hand side is true. Well, if we're looking at the n equals 1 term on the left-hand side, then it's just basically the first term. So the first term happens to have the value 1. So we're going to write down the value 1 here to check the left-hand side. And then the right-hand side, when n equals 1, we just simply replace the n's with the value 1. So this becomes 1 times 1 plus 1 divided by 2. And then we just are simply checking to see if the right-hand side is equal to the left-hand side for this base case. 1 plus 1 is 2. We multiply that by the 1 on the left here, divide that by the 2 on the bottom. 1 times 2 is 2, divided by the 2 on the bottom is simply equal to 1. So for the base case for n equals 1, we have basically 1 on the left-hand side equals 1 on the right-hand side. So I think that's simple enough. We can just erase it. So basically for the basis case we have 1 equals 1, and that is a true statement. And so since the basis case is true, we can proceed to the next step. So the next step is going to be the induction step. And basically what we're going to do with the induction step is we're going to do a couple things. We're basically just going to assume that this statement is true for some value n equals k. So we're going to assume that it's true for n equals k. And so basically let's go ahead and do that now. Let's just say that we have 1 plus, let's write it over here to give myself some more room. So basically for this step we have 1 plus 2 plus 3 plus all the way up to some value k. We're saying that we're just going to assume that that's equal to the right hand side, so plugging in k where n's are, k plus 1 divided by 2. So we've assumed that this is true, and so then the next thing we want to do is we want to show that it is true for n is equal to k plus 1. So we've assumed this step is true for n equals k. We're going to show that it's true for n equals k plus 1, and we're going to do that based off of this assumption. So for n equals k plus 1, we basically have 1 plus 2 plus 3 plus all the way up to k, and then we go one more further to k plus 1. And then we're going to also plug in k plus 1 where the n's are here. So this is going to be k plus 1 for that part. And that's multiplied by k plus 1, plugging that in where the n is. And then we have plus 1. We could put this in parentheses to kind of set it apart, but really we're just going to be adding these anyway, so I'm just going to leave it like this. And we're going to divide that by the 2 here. So we're assuming this is true, and we're going to show that this is true based off of this assumption. So what we're going to do with this assumption is, if you notice right here we have 1 all the way up to k, so that's the same as what we have right here. And since we're assuming this is true, then we're basically saying that this right here we can use to replace this, because these are the same. So we're just going to replace all this stuff with the right hand side of this assumption. So this becomes k times k plus 1 divided by 2, and then we add that to the k plus 1 over here, and then we're just going to check, is that equal to k plus 1, and then here this is really k plus 1 or k plus 2 divided by the 2. And then one more thing I want to do is, notice how this is divided by 2, this is divided by 2. I'd like to make a denominator of 2 as well to match for this term, so I'm simply just going to multiply this by the number 1, and I'm going to choose 2 divided by 2 to be my number 1. Since 2 divided by 2 is equal to 1, I just multiplied this by 1. Anything times 1 doesn't change its value. So now I have all 3 of these terms with the same common denominator. So basically, if we can show that this statement is true now, then we've basically completed the mathematical induction proof. So if you notice, all of these are 2 now. We don't even really need to look at the denominators. They're all the same. So now if we can just show that the numerators are the same, then we've basically completed the proof. So let's just rewrite the numerators to make this a little bit more simple. K times k plus 1 plus 2 times k plus 1 is equal to k plus 1 times k plus 2. So now we're just going to just make sure that the numerators are the same, since we already know the denominators are the same. So k times k is k squared, and then we do the plus, distributing the k to the second term, k times 1 is k. And then we're going to add that to 2 times k, and then the plus, distributing the 2 to the next term, 2 times 1 is 2. Is that equal to, this is going to be basically a FOIL, so k distributed into the k is k squared, and then we do the plus sign, k distributed into the 2 is 2k, and then for the next term, 1 times k is equal to k, 1 times the positive 2 is going to be positive 2. So now if we look on the left hand side, we have a k squared, we have a k squared on the right hand side. On the left hand side we have a k, on the right hand side we have a k. on the left-hand side we have a 2k, on the right-hand side we also have a 2k, and we also have the number 2 on both the left and the right-hand side. So we've basically showed that this is true for n equals k plus 1, and we did that based off of the assumption that it is true for n equals k. And we've checked the basis step to show that it works for at least the most simple case, and basically that is the entire proof right there. We have now proved that this statement is true by mathematical induction. So anyway, thanks for watching, and stay tuned for some more educational math videos.